In an infrared spectrum, some signals may be very strong in comparison with other signals on the same spectrum. That is, some bonds absorb infrared radiation very efficiently, while other bonds are less efficient at absorbing infrared radiation. To understand this, you got to consider how the strength of the dipole moment changes when a bond vibrates. Recall that dipole moment mu is defined by this equation. Mu is equal to E times D, where E is the strength of the partial charges, delta plus and delta minus, and D is the distance separating those partial charges. Now consider what happens to the strength of the dipole moment as a bond stretches. As a bond vibrates, the distance between the partial charges is constantly changing, which means that the strength of the dipole moment also changes with time. A plot of dipole moment as a function of time shows an oscillating dipole moment, as is shown in both of these graphs here. The dipole moment is an electric field surrounding the bond. So as the dipole moment oscillates, the bond is essentially surrounded by an oscillating electric field, which serves as an antenna, so to speak, for absorbing infrared radiation. Since electromagnetic radiation itself is comprised of an oscillating electric field, the bond can absorb a photon because the bond's oscillating electric field interacts with the oscillating electric field of the infrared radiation. The efficiency of a bond at absorbing infrared radiation therefore depends on the strength of the dipole moment. For example, compare these two bonds, the carbonyl and this carbon-carbon double bond. Each of these bonds has a measurable dipole moment, however, they differ significantly in strength. If we look at the carbonyl group, due to resonance and induction, the carbon atom bears a large partial positive charge, and the oxygen atom bears a large partial negative charge. The carbonyl group therefore has a large dipole moment. Now if we look at the carbon-carbon double bond, one vinylic position is connected to two alkyl groups, while the other vinylic position is connected to two hydrogen atoms. As such, the two vinylic positions are not electronically identical, so the dipole moment is going to be very small. The oscillating electric field associated with the carbonyl group is much stronger than the oscillating field associated with the carbon-carbon bond. Therefore, the carbonyl group functions as a better antenna for absorbing infrared radiation. That is, the carbonyl group is more efficient at absorbing infrared radiation, producing a stronger signal. Carbonyl groups often produce the strongest signals in an infrared spectrum, while carbon-carbon double bonds often produce fairly weak signals. In fact, some alkenes do not even produce any carbon-carbon double bond signal at all. For example, consider the infrared spectrum of 2,3-dimethyl-2-butene shown here. This alkene is symmetrical, that is, both vinylic positions are electronically identical, and the bond has no dipole moment at all. As the carbon-carbon double bond vibrates, there's no change in the dipole moment, which means that the bond cannot function as an antenna for absorbing infrared radiation. In other words, symmetrical bonds are completely inefficient at absorbing infrared radiation, and no signal is observed. The same is true for symmetrical carbon-carbon triple bonds. And so the take-home message is that the stronger the dipole, the stronger the signal. The weaker the dipole, the weaker the signal.